So today is going to be our last dedicated session on the uncertainty principle. And as we all know that if we have a wave function for any particle, an electron, a proton, a photon, a neutron, which is a sine wave like this, and which extends from minus infinity to plus infinity, then the uncertainty in its position, delta x, is extremely large, which means that before you measure the position of the particle is really everywhere. There is a huge realm of possibilities for the position of the particle, but the momentum is fixed. So there is one precise momentum, P naught, which equals h bar k naught, which equals h bar 2 pi over lambda, or h over lambda, and lambda is the wavelength of this wave function, and this wave function is plotted as a function of x. And if you would like to plot what is happening on a position momentum coordinate frame, the uncertainty in position is extremely large and the uncertainty in momentum is virtually zero, which means that there is a huge realm of possibilities for the position, and there is only one possibility for what you measure for the momentum. So the diagram, the position momentum diagram, looks like this before measurement, and once you measure the position, this wave function collapses, and you measure a precise momentum. You measure a particular value of the position, you measure a particular value of the position, and that position could be any one of this very large range of possibilities. So you can measure this position, you can measure this position, you can measure the position to be zero anywhere. So you measure a definite position, which is one of the infinite possibilities of the position, and in the process the momentum becomes totally uncertain. So your wave function collapses upon measurement of the position. But if for this wave function, if for this wave function you measure the momentum, the wave function will not collapse. So this is something that we've already seen about the uncertainty principle. Now let's build this concept a little bit further. If we had a wave function psi of x which looks like this, so if this is the wave function at any time, what is the range of possibilities of x? Is the uncertainty in x infinite? No, it's finite. This wave function is zero everywhere, but it's non-zero only in this small region. So if I were to define an uncertainty in position, which defines the range of possibilities of position that you would measure when you make an experiment, I can define this to be the uncertainty in position delta x. So this is my choice, what I would like to define. I could define the width of this central maximum to be delta x. I could define the entire width to be delta x. I could define anything I like. Alright, so it's a subjective decision that you make. How do you define delta x? So now I've defined delta x. If I measure the position of this particle, I could measure an x which corresponds to this value, to this value, to this value, to this value, with certain probabilities. And those probabilities will be given by the modulus squared of this wave function. So if I take this wave function and plot the modulus squared, I might get something like this. All the negative values turn positive. And this is the spread of the values of delta x. Now can we define a precise momentum for this wave function? No. There also has to be a corresponding spread in the momenta, or a realm of possibilities for the momenta. For example, if I were to plot this wave function in the momentum space, there is a range of possibilities for the momentum. And how are these wave functions related? This is the Fourier integral of this function, and this is the inverse Fourier integral of this function, or vice versa. So if there is a range of possibilities of x, there has to be a range of possibilities of momentum. Now let's try to draw a curve of this kind, a position momentum diagram, and see what do we obtain. But let's try to simplify this problem a little bit further. Suppose our wave function psi x is a Gaussian function like this. Like, you will not find this in your textbook, so please pay attention. Suppose this is my wave function. I have to define an uncertainty in the position. So there are different ways in which I can define the uncertainty. It's my subjective choice. This is a Gaussian function, so the function never really goes to 0. It becomes very small, but it never really goes to 0. Okay? So I have to choose my uncertainty, my realm of possibilities for x. There are different ways I can choose my uncertainty. I can take this maximum value a and see where the amplitude of this wave function is half of its maximum value, a by 2, and then take the corresponding positions x and find the difference between these positions. This becomes my delta x. So this is one way of defining the delta x. This delta x is called the full width half maximum. The full width at half of the maximum. So this is one way of defining delta x. Another way of defining delta x could be this function has some mean value and it has some standard deviation. So I can define the standard deviation of this function, the standard deviation, to be delta x. So it's my choice. How would I like to define my uncertainty in position, or the realm of possibilities of position? So it's a subjective choice. How do I define delta x? Now suppose this delta x, I choose this definition, and this delta x really is 10 nanometers. Okay? And I'm measuring the position of this particle with a position detector whose resolution is 1 nanometers. Now do you understand what is meant by resolution?
You can look at 1 nanometer.
It's the least count of the measurement device. For example, a meter scale has a resolution of perhaps 1 centimeters. A smaller scale could have a resolution of 1 millimeters. A micrometer screw gauge can have a resolution of 1 micron. So this is the smallest division a measuring instrument can measure. Now this is my wave function with a realm of possibilities of x, and this realm is of length 10 nanometers, and I'm measuring the position of this object with a device whose resolution is 1 nanometers. Do you understand the problem? Okay. Now I would like to draw a graph of this kind. What happens when we make a measurement? This is X, this is P, and suppose this central value is, say, 20 nanometers. This wave function has a peak at 20 nanometers and the spread of the values of delta X is 10 nanometers. So this point is 25 nanometers and this point is 15 nanometers. So this is the definition of the wave function. Now I'm measuring the position of this particle with a detector with a resolution of 1 nanometers. I have one particle, a single electron, okay, and I measure the position of this electron with my hypothetical device. What should I get on this graph? Could you please think a little bit about it and show me what you would get in a single measurement, in a single electron? Could you identify whether I should get a blob here? How big should be that blob? And so on. I'm just making a single measurement, one observation. अच्छा, जो स्ट्रेट लाइन बनाई है इसकी विड्थ क्या है और ये कहाँ पर है ये स्ट्रेट लाइन? तो ये इसकी विड्थ कितनी है?
विड्थ इंपॉर्टेंट।
बिल्कुल। कितनी होगी? कितनी होगी नैनोमीटर्स में? तो 10 नैनोमीटर्स विड्थ होगी सिंगल पॉइंट की, 1 नैनोमीटर्स होगी। Where is this line located?
Anywhere in delta X.
जब तक आप हाथ से करोगे नहीं क्लास में, फिर आप ये ना पूछना मैं क्विज की तैयारी कैसे करूं। क्विज की तैयारी क्लास में होती है। This is 10 nanometers. It can't be 10 nanometers in a single. Your detector cannot measure with the resolution higher than 1 nanometer. It has a resolution of 1 nanometer, so it's going to measure some position plus minus 1 nanometers. So what the detector is really going to measure is, it's going to collapse this wave function and you get a possibilities of X. That X could be anywhere between, say, 15 nanometers and 25 nanometers. In fact, it could even be smaller than 15 nanometers with some probability, with a very little probability. But there's a higher likelihood that it will fall in this regime. So if I mark the point 20 nanometers here and I draw a hypothetical line at 15 nanometers and a hypothetical line at 25 nanometers, then my detector will observe the electron to be somewhere in between these lines. Okay? It will click with a maximum probability at 20 nanometers because here the probability density function is maximum, but it could be anywhere between these hypothetical lines. But the detector has a resolution of 1 nanometers. So what I will get a line or a region anywhere between these hypothetical lines. This region has a width of 1 nanometers. And the momentum becomes uncertain. So this width is 1 nanometers. So this is the result of a single measurement, the outcome of a single measurement. Now I have an identical electron. Okay? An electron that is prepared in the same way, it has the same energy, which means it has the same wave function. And I have an identical detector. In other words, I'm repeating the experiment with a clone of the original electron. Because in order to observe probabilities, you have to repeat the experiment. Just by looking at this, you cannot tell what the wave function is. If this is unknown and you make this observation, you're a mortal human being, an experimenter who's observing an electron. You don't know what the wave function is. You have to work your way backwards to find out what the wave function is. You can't do it in a single go. You cannot do it in a single shot. That is, you just make one measurement and you're able to tell what the wave function is. So now you repeat the experiment on an identical electron. You can't repeat the experiment on the same electron in most cases because the electron now has a new wave function. Okay, so now you somehow from the store, from some reservoir, you get an identical electron and perform an identical experiment. You get another observation somewhere within the same region, a width of 1 nanometers, but it could be some other position. Okay? It could be some other position. It could be anywhere inside these hypothetical lines. In fact, there is a finite probability that this electron is observed outside these lines because here the wave function is not actually disappearing. There is a finite, these tails are very long. So at the end, after you repeat the experiment a large number of times, you will build up this graph. You will start building up the position momentum diagram. And after repeated experiments, your position momentum diagram could look something like this. Where this is your delta x. The width of this blob is delta x. It will represent this delta x. It's going to be about 10 nanometers. This total width is going to be about 10 nanometers. And this width could be about delta p, the uncertainty in the momentum. So this is how you build up a position momentum diagram. And now, one thing I would like to emphasize again is that if you perform a single measurement, it is the resolution of the detector that determines how precise a measurement you can make. The uncertainty in position was 10 nanometers, but in a single measurement you could go down to 1 nanometers. But that does not mean that the electron is located within this 1 nanometers. If you repeat the experiment, the electron appears somewhere else. Okay? So the electron is not confined in this 1 nanometers. One shot or one measurement cannot reveal the true position of an electron, because the electron does not have a true position. If you measure the electron to be here, you cannot say that the electron existed at this point. It just happened that the field collapsed and gave you a reading at this point. Okay, so this is the uncertainty principle. Now, a few applications, some very interesting applications. One question: if you buy a more expensive detector, is a micrometer screw gauge more expensive than a meter rule? Yes, because it has a better resolution, it has a finer resolution. Now if someone were to give you money and ask you to buy a detector whose resolution is 1 angstroms, what's going to happen? If you take a single measurement, X, P, you take a single measurement, you'll obtain a fine line, a finer line of width 1 angstrom. 1 angstrom is 1/10 of a nanometers. You obtain a finer line, but then you repeat the experiment, you still obtain the same curve, you still obtain the same uncertainty in the position. Alright? So a finer detector, a more expensive detector, a detector with a finer resolution cannot let you break away from the confines of the uncertainty principle. ये uncertainty principle एक कैद खाना है, एक prison है, हमें उसके अंदर रहना है. We cannot break loose from this prison. This is a fundamental restriction imposed upon us by nature. We cannot free ourselves from the confines of the uncertainty principle. No matter how good a detector we can build, no matter how good an experimenter we are, even if you are Michael Faraday, whom I think was one of the greatest experimenters of all times, we cannot surpass the uncertainty principle. Alright? So this is something that is within the quantum nature of our universe. Okay? It's intrinsic. That's why I call it intrinsic uncertainty. It has nothing to do with the finitude of human beings. Nothing to do with our incapacity of making perfect measurements. खामोशी से सुने, मुझे पता है आपको बहुत मजा आ रहा है, आप बहुत मुस्कुरा रहे हैं, but you really have to pay attention. Alright, now let's move to another experiment. The uncertainty principle from the perspective of the single slit. Suppose I have a screen with just one slit, and this slit has width A, and here I have a screen. So single electrons or single photons come in one at a time. What will you observe on the screen? A single slit diffraction pattern. This is what you will observe on the screen. Now electrons or protons or photons or neutrons or buckyballs or bacteria or anything that you would like to do a diffraction experiment with are coming in. All of these particles are identical and they're acting like matter waves, so they have some wavelength lambda, and they're moving in this direction, all of them. Suppose I have an axis, I draw axes, I call this X and I call this Z. Alright. Now all the electrons are moving in the z direction. They will have a certain wavelength and they will have a certain momentum. All of them are identical. So their momentum will be pz, and that will be given by h over lambda. Alright? ठीक है? Now the problem is that if these electrons, all of them were coming in a straight line, they were just moving along z, you will never observe an electron striking here, or striking here, or striking here. All of the electrons should come up here. But you observe a diffraction fringe. So some electrons do reach this point, some electrons do reach this point, and some electrons do reach this point. No electron, of course, reaches this minimum or this minimum. So the electron must have some px as well. Okay? Agreed?
Yes.
It must have some momentum along the x direction, which enables the electron to reach points away from the central maximum. Alright, fine. Now by looking at the electrons that are coming out of the slit, if we do not observe the electrons, we do not have any detector that is focused on this slit, do we know where the electrons are coming out of the slit? You see, this slit has some width. Do you know where the electron is actually coming out? What's the position of the electron as it comes out of the slit? No, we have no idea about it. So there is some uncertainty in the position of the electron as it comes out of the slit. That uncertainty is delta x, and that's given by the width of the slit. We don't know anything about where the electron is actually coming out of this slit. So there is complete ignorance as to the exact location of the electron inside this slit. Agreed? So there's a realm of possibilities. If I ask you the question, where is the electron inside this slit, you cannot tell. There's a range of possibilities, and that range of possibilities equals the slit width. Okay? आपको बात समझ आई? आपको मुझे लगता है समझ नहीं आई. आप जी समझ आ गई बात? So this range of possibilities, delta x equals the width slit, because we are ignorant of where the electron precisely is inside the slit. So there is some delta x. Now the electron can fall anywhere inside this central lobe. Let's for the time being ignore these small lobes. So the electron can fall anywhere in this range, in this regime. Okay? Which means it can have a momentum like this, which makes it go straight through, right to the central maximum. It can have this momentum, it can have this momentum, and at the extremities it can have this momentum. So the momentum of the electron could be either this one, this one, this one, this one. These arrows define the extremities of the momentum. Extremities means hadde, hudud, the extreme values of the momentum. Alright? So there is some uncertainty in the momentum as well, because there is a range of possibilities of the momentum. ठीक है, याद रखें कि जो मैंने आपको अनसर्टेनिटी बताया ना, रेंज ऑफ पॉसिबिलिटीज, इससे बहुत सहूलत होगी आपको समझने में कि व्हाट इज अनसर्टेनिटी. अनसर्टेनिटी इज अ रियल्म ऑफ पॉसिबिलिटीज. सो देयर इज अ रियल्म ऑफ पॉसिबिलिटीज फॉर द मोमेंटम. ओके, सो इफ दिस एंगल is theta, if this angle is theta, can you please tell me if this is a minimum, if this is a minimum and the wavelength is lambda, can you find out what this theta should be? Remember your recitation from the single slit diffraction. I would like to, if this is your slit width, this is a minimum, the wavelength is lambda, what is this theta? n क्या है?
1 ले लो,
1 नहीं है ना यहाँ पे,
lambda होने में,
लैम्डा ओवर ए इज साइन थीटा.
sin theta और theta ही होगा.
एक भी आएगा यहाँ पे कहीं पे, ए है या a/2 है? So I'm drawing another diagram, an exaggerated version of the slit so that I can explain what's happening. This slit width is A, and suppose this is a point of the minimum. Now what this means is I divide this slit into two parts, hypothetically. Okay? What this means that if there is a ray from, if there is a ray from this edge that goes up to the minimum, and there is a ray, a corresponding ray from the middle of the slit that goes to this point, I call this ray 1, I call this ray 1 dash, and 1 dash destructively interfere. Okay, then I draw another ray just below this one, goes to the same point, and I draw another ray beneath the middle point, goes to the same point, and this ray, new ray 2 and the new ray 2 dash destructively interfere. So all the rays from the top half of the slit are destructively interfering with rays from the bottom half of the slit. Now what is the path difference between the ray 1 and 1 dash? It's a/2 sine theta, because this distance, the distance between ray 1 and 1 dash is a/2, the distance between 2 and 2 dash is a/2, the distance between 3 and 3 dash is a/2, and so on. So if this path difference equals lambda by 2, then this is the condition for destructive interference taking place here. So this 2 cancels out, and I'm left with a sine theta equals lambda, or sine theta equals lambda over a. This is the condition for destructive interference. At this value of theta will the first minimum appear. Now if you look at this momentum vector has two components. It has a pz and a px. Okay? And this momentum vector has a length p. This angle of course is theta. So what is the value of px? For this particular momentum vector, what is the value of px? G? P sine theta. So for this particular vector, Px equals P sine theta. So this is one extreme momentum, Px. This is the x component of the momentum at the extreme, at the edge of the range of the momenta. And this is the other edge. This is the other extreme value of the momentum. So what is the value of Px for this momentum vector? It's going to be P sine of minus theta, or minus P sine theta. So all your P vectors have an x component that ranges between plus P sine theta and minus P sine theta. What's the x component of this momentum vector? 0. So the x components range between P sine theta and minus P sine theta. Okay? So what is your delta Px? What is the total range, the total span, the total realm of possibilities of Px? It's 2P sine theta. So let's multiply delta x with delta Px. This is 2P sine theta. What is P? H over lambda. What is sine theta? Lambda over A. You get 2H. So if I decrease the slit width, if I decrease delta x, this goes down, this must go up. And what this physically means, if I decrease this slit width, this fringe will become broader. Again the same concept. The conjugacy, the seesaw relationship between position and momentum, between x and p. If I reduce this further, this peak will even become broader. And it is evident from this relationship. If I increase A, slit becomes wider, this peak becomes tighter and tighter, which means that most of the electrons will have the same px, and that will be almost 0. Most of the electrons will go straight through without being diffracted, without being bent. So everything is making coherent sense, everything is fitting in together. All the pieces of the jigsaw puzzle, they are starting appearing like a beautiful picture. And this relationship, the conjugate, the seesaw relationship between x and p, we've seen it in many different ways, starting from our discussion on waves, on Fourier integrals. It's the same concept. X goes down, p goes up. P goes down, x goes up. Sorry, delta x and delta p, really. And this equals some constant. What Heisenberg in 1923 almost, what he showed is that delta x, delta px has to be greater than or equal to some constant. And he called this constant h bar over 2, because he defined his delta x in a special way. He defined these by standard deviations. But don't worry too much about whether there is a factor of 2 here or not. It doesn't really make much of a difference, because this h bar is really very small. You divide it by 2, it doesn't make much of a difference. And this 2h is of course greater than this h bar over 2. This h bar over 2 is h over 4 pi. Right? So this of course is greater than this. So this satisfies this inequality. Remember, this is not an equality, it's an inequality. This left hand side has to be greater than the right hand side. And this condition, this experiment that I've shown you, satisfies the Heisenberg's uncertainty principle. And with the help of the Heisenberg's uncertainty principle, we can make order of magnitude estimates of what delta x should be, what delta p should be. Okay? Without knowing what the wave function is. So it's a very powerful tool, the uncertainty principle. And now I've given you enough, I've in fact belabored the point or hammered in the point what the uncertainty principle really means. And these position momentum diagrams are really a very useful aid in understanding the uncertainty principle. Okay? So do remember that a single measurement can give you a peak position that is smaller than the uncertainty. But then you repeat the experiment, you build up your smear of points. Alright. There is also a physical interpretation of uncertainty. शायद इसकी बारी ना आए. Let's see. अभी तक कोई सवाल? कोई सवाल? इतनी ज़्यादा टेक्निकल डिटेल्स में नहीं जाने की ज़रूरत. ये स्क्वायर, ये डिपेंड्स अपॉन द डिटेक्टर, डिपेंड्स अपॉन द काइंड ऑफ मेजरमेंट दैट यू मेक एंड सो. ठीक है. कॉन्सेप्चुअल डायग्राम है, डोंट टेक इट टू लिटरली. Now there is also an, आप जो आखिर में दोनों बैठी हुई है ना, I think you're having a very good time. घड़ी के पास भी बैठी हुई हैं. So relativity says that you closer to a watch, probably time will pass faster for you. No, it won't. अच्छा, अब देखो एक फिजिकल इंटरप्रिटेशन भी है, एटॉमिस्टिक इंटरप्रिटेशन अनसर्टेनिटी प्रिंसिपल की. और ये सिर्फ इंटरप्रिटेशन है. इंटरप्रिटेशन का क्या मतलब होता है फिजिक्स में? समथिंग दैट सैटिस्फाइज योर हार्ट. It may or may not be true, but you interpret it that way. The collapse of a wave function is an interpretation. It's an interpretation. So जब आप quantum mechanics में आते हैं, तो there is a little bit of philosophy involved as well. Interpretative aspects to quantum mechanics. Some people say that the wave function does not collapse. So you are in a universe, right? This is your universe. It's like a tube. Okay, your universe is a tube, and if आपका नाम क्या? Bilal. Ahmed Bilal. If Bilal observes the wave function such that he collapses, suppose there's a cat, right? Called the Schrodinger's cat, and that cat is inside a box, and there's a poison vial inside the box. There's a radioactive atom. When radioactivity decay occurs, a hammer is activated that breaks the vial of poison. The poison spreads and the cat dies. So if this cat is inside a black box, before you open the box, you don't know whether the cat is alive or dead. Quantum mechanics tells you that the cat is in a superposition. It's both alive and dead at the same time. Right? It's true. I mean, you can observe this behavior for electrons, for photons, why not for a cat? It just becomes more difficult to observe, but there's a superposition for the cat. Now if Mr. Bilal opens the box and he observes the cat to be alive, which means that the radioactive atom has not yet decayed because it's a random process, then this universe, this Bilal's universe, is going to split into two. So when you open the box, this universe is going to split into two branches, and this branch in which Bilal sees an alive cat is where Mr. Bilal lives. But there is a Mr. Anti-Bilal in a parallel universe who sees the same cat to be dead. So this is another interpretation, and I'm not joking about it. The problem with this interpretation is that you can't prove or disprove it. This interpretation is called the many worlds interpretation of measurement. So one interpretation of the uncertainty principle is that if you have an electron, for example, and you want to observe the position of this electron is moving with a speed Vx. Khamoshi say, this electron is moving with the speed Vx. Now you want to observe the position of this electron. It's moving and you want to see where it is. Right? So you need some kind of detector. आपको इल्हाम तो नहीं होगा कि कहाँ पे इलेक्ट्रॉन, आपको देखना पड़ेगा, कोई डिटेक्टर लाना पड़ेगा या खुद आंखों से देखना पड़ेगा, उसको किसी तरह ऑब्जर्व करना पड़ेगा. The experiment changes, as I've given you numerous examples of this. So what you would like to do, you will shine photons on it. A photon has energy and frequency hf. It has a momentum. The photon also has a momentum h over lambda. So this photon strikes the electron, right? This is a probing photon. Probe का मतलब आपने एक मैसेंजर भेजा है, इलेक्ट्रॉन को देख के आओ, उसकी खबर मुझे लाके दो. ठीक है? So this photon goes to the electron. It has some momentum of its own. Now it must interact with the electron, and the collision or the scattering process will take place. So this has momentum, this electron has momentum, momentum will be shared. An elastic collision is going to take place. Suppose this photon, after interacting with the electron, comes back with a new frequency f dash and a new wavelength lambda dash, and it comes into your eye, the observer, and this photon now wants to tell, this photon is a messenger of the position of the electron. Now what's going to happen is that this photon, the initial photon, the incident photon carries momentum. It's going to give a kick to the electron to the other side. Okay? It's giving a kick to the electron to the other side. Therefore this electron will, its initial position was here. This electron can take a kick to the back side and its position becomes uncertain. This electron takes a kick to the back side, so this photon cannot tell the initial position of the electron, because now this is what the photon will tell you. It will tell you that the electron could be anywhere in this location, in this delta x. Because the photon carries momentum and it disturbs the electron and transfers momentum to the electron, as a result the position of this electron becomes uncertain. Okay? So now let's look at this a little bit in more mathematical detail. The uncertainty in the position of the electron, which is something you would like to measure. That's why you're sending the probe photon. The maximum value of this uncertainty could be Vx times delta t. If this electron, which was moving to the right with the velocity Vx, suddenly changes its direction altogether, so that its velocity now becomes Vx in the other direction. ये हो सकता है ना? This is the extreme case. We're looking at the extreme case. The electron shifts its direction altogether because it has been come and bombarded by a photon. Now its velocity is Vx, but in the opposite direction. And if this photon interacts with the electron for a time delta t, then the uncertainty in the position of the electron is going to be delta x. Okay? Now the energy of the electron is p square 2m. Since there is a delta x, there has to be an uncertainty in the momentum as well, because of the uncertainty principle. And if p is uncertain, energy is going to be uncertain. Okay? So if you know that delta x, delta p is greater than or equal to some constant, suppose this equals, I would say, h. Suppose this is equal to h. It's of course greater than or equal to h bar over 2. Now if I look at this expression and I would like to find out the uncertainty in the energy, what would I do? I would take the derivative of this 2p delta p divided by 2m. Okay? Do you understand this point? ये किसको समझ नहीं आया? आपको समझ नहीं आया, ठीक है? आपने अनसर्टेनिटी एनालिसिस पढ़ा हुआ है? एरर एनालिसिस ए लेवल्स में? If I replace p by p plus delta p and I put p plus delta p into this expression, my energy will become E plus delta E. And then I can solve this equation and find out what delta E is. Delta E, have you studied differentials in your calculus 1? If y equals x squared, what is dy? It's 2x dx. Now what is this dx? It's a small interval in x. Okay? And what is this dy? It's a small interval in y. So delta y is 2x delta x. I've done the same thing here. This is p square. I take the differential 2p into delta p. Okay, this 2m just remains there. This 2 cancels out. Now what is p over m? P over m is the velocity. So delta E equals Vx delta p. All right. Now I take delta x delta p. This is greater than or equal to h bar over 2, correct? from the uncertainty principle. I take delta x from here, I call it, this becomes Vx delta t. Delta p I take from here, this becomes delta E over Vx. This must be greater than or equal to h bar over 2. Simple algebra. So this Vx cancels out. I have this relationship, delta E delta t greater than equal to h bar over 2. Alright, so this is the Heisenberg's uncertainty principle. This is also the Heisenberg's uncertainty principle. This tells us that position and momentum are C variables. Delta x, delta p. This tells us that delta t and delta E are seesaw variables. Both of these are different versions of the uncertainty principle. This tells us that if there is a realm of possibilities of x, there is going to be a realm of possibilities of delta p. If the possibilities for x shrinks, the possibilities for momentum go up. Now what this tells us is that if you would like to precisely measure the energy, you need a very long time for it. Alright? If you want to precisely measure the energy, you need a very long time for it. Now this is slightly confusing and slightly subtle. There are some concepts in physics that are subtle, that are sophisticated in the sense that are difficult to understand in first go. This is one of them. But let me try to give you an idea of what this uncertainty principle means. Suppose if you have a particle with a certain energy, like a photon, what property of the photon tells you what the energy is? Is it the frequency? Correct? It's the frequency. Okay? So the frequency is a measure of the energy. If I draw the wave for a photon, and this axis is now the time axis. So this is the wave of a photon and this axis is the time axis. Can you tell me what the frequency is? You can find the time period. You can find the time period, and the inverse of this time period will be the frequency. So you can find the frequency, you can find omega, you can find the energy. But the problem is that if you really want to be sure about the frequency of this wave has to continue for a very long time. Alright, now how do I validate my statement? If I have something that continues for a very long time, this is the time axis now. Suppose I draw this wave that goes from minus infinity to plus infinity, from eternity to eternity, very long wave. ठीक है? I can precisely determine what its frequency is. Just like if this were position, I can precisely tell what the momentum is. Okay? अगर यहाँ पर मैं position लिखता, तो I can tell what the wavelength is precisely, which means I can tell what the momentum is. Okay? So if I draw a position momentum diagram, x, p, I can precisely tell what the momentum is, but I cannot tell anything about the position. Likewise, for this particular diagram, I have time here and I have frequency or energy here. Can I tell the time of this wave? At what time was the wave emitted? No, because this wave was emitted at minus infinity. It goes to minus infinity. I am completely uncertain about the time. This time, in other words, is very long. The delta t is very long. The possibilities of time is very long. But the frequency is precisely known, which means the energy is precisely known. So I can draw a curve like this. So there is a relationship between x and p, and an exactly similar relationship exists between time and energy. Now if I have this graph, it has a precise energy, it has a precise frequency. On the other hand, if I draw something like this, this is time. So I have a laser or a light bulb. Off, it goes off, right? Photons don't come out of the bulb, and I turn it on, off, on, off, on. Now this is the condition which is represented by this graph. There's an off condition, then there's an on condition and an off condition. Can I tell what the frequency of this wave is? No. I cannot tell what the energy of this wave is. What is the energy of the photon that is carrying this wave? I cannot be precise about it. There is a spread in the energy and there is a spread in the time. So if I want to precisely know what the energy is, I would need infinite time for it. Alright? So how do I justify this fact? For this I've made a demonstration, but probably I'm going to show you the first thing tomorrow morning at 9 a.m. But let's look at the following. Run out of blackboard. Suppose I have an atom in which the energy levels are quantized. Okay? Now is this energy fixed? Suppose these are levels in a hydrogen atom. Is this energy fixed? Yes. So if this is the lowest level, this could be minus 13.6 electron volts. If this is the first excited state, what's the energy of this excited state? Minus 3.4 electron volts. Alright. Is this energy fixed? जब हमने Bohr's model derive किया था, did we get a precise value of the energy? Yes. We got a precise value of the energy. Right? There was no uncertainty in it. That's how we derived the Bohr's model. Agreed? याद है ना Bohr's model? Which means that if an electron sits in this first excited state and it would like to come down because it's in an excited state, then a wave is emitted or photons are emitted, and these photons have an energy E photon which exactly equals exactly, I'm putting it really exactly, E2 minus E1. But if you observe the spectrum, like something I would have liked to show you today. This is the frequency or the wavelength axis. This is the intensity axis. So a precise frequency would also mean a precise wavelength, right? A precise wavelength. So what I should ideally see is a sharp peak. At this wavelength, lambda naught. Okay, this is something I should actually see, because these energies are precise. If the energies are precise, the energy difference is precise. There is no uncertainty about it. There is no ignorance about it. You know everything there is to be known about it. Right? There is no imprecision about it. It's certain. There is no uncertainty. There is only one possibility. There is no realm of possibilities. So this should be a single sharp line, just at lambda naught. But what we really observe are peaks. Peaks like this. So there is a finite width of the peak, which means that there are some photons that are being emitted, or there are some photons that are being detected. You don't know what's going on. You're detecting photons. So some photons are being detected with higher frequencies or higher wavelengths, and some of them with shorter wavelengths. But where are these photons coming from?
Vibrational levels.
No, they're not coming from vibrational levels. If these are purely electronic energy levels, no vibrational levels, no rotational levels. This finite line width is explained by the energy time uncertainty principle. If the electron, if you would like to have finer and finer lines, that you would like to have this peak sharper and finer and narrower, which means you would like to have a precise frequency, a precise energy, or you would like to reduce this delta E. If you would like to reduce this delta E, this delta T has to go up, which means that the electron has to spend more and more time in the state above. And if you would really like to have an extremely sharp peak, this electron should never fall down. It should stay in the higher level for a very long time. Right? So I'll have more to say about this in tomorrow's class. So inshallah, see you tomorrow. We're going to show us tomorrow.